is sometimes reported in weight volume percent. We have different percentages. And it depends on how we represent these. Since I have limited time, I didn't discuss this quite yet. But when we have percentages, ppm, ppb, etc., oftentimes what we'll do is we'll do something like this: WV, or WW, or W. Weight volume. Actually, not W. Let's go with M over M, or V over V. These are all different kinds of percentages. And so W and M are the same, weight and mass, and treat them the same. And so this is a mass over volume percent. This is a mass over mass percent, volume over volume percent. We have lots of different percentages. In biology, one of these is used quite often, and that's a WV percent. WV percent is like 0.9% sodium chloride. This is a WV percent. Have you heard of 0.9% sodium chloride or saline solution? This is what they call isotonic with blood. Saline solution. And this is often given intravenously. But what it means is what? Is it M over V? Yeah, I think it's M over V. What does this mean? 0.9% WV.
0.9% of a whole solution is salt or NaCl.
No, yeah, right. But what we do is we always convert all these, whether it's percent, ppm, ppb, we convert it into fractional form. We convert it into fractional form to use as a conversion factor. Right? And so this would be grams of sodium chloride per 100 grams of what? Solution, yeah. Actually, is that quite correct? Because if it's a V, then it's not quite correct. Because the V, this is normally, our normal one would be this, but these are different. If it's a V, we wouldn't do grams, we do milliliters here. Something like that. I need to check that to see. But a milliliter of water, 100 milliliters of water is about how many grams? It's about 100 grams. So if you have 100 milliliters of water, it's about 100 grams. However, that's only if the density is right at 1. If the density is slightly above 1 or whatever, then it will be slightly off. And so in this case, it's going to be close because if we have, it's a salt solution, so density is going to be a little higher than pure water. So it's going to be awfully close to 0.9% by mass. And so the first thing we do in these types of problems is we look at all the conversion factors that are given. And so I had a question about this the other day, and the people, this student wasn't including any units in their calculation. They're just doing all the calculations in their head, which would, to me, be pretty difficult thing to do. So let me paste that in there. See where I'm at. All right, so the first thing is we dig out all the information. And so this is a weight volume percent. And so if you see 0.10%, how do you write that in fractional form? 0.10 per 100. But now we have to include the units. If you don't include the units, you're going to be in trouble. But they tell us, I mean, they give us a hint here. It's going to be 0.10 grams of ethyl alcohol. Ethyl alcohol, let's talk about ethyl alcohol. Ethyl alcohol has how many carbons? 2. And do you guys remember what a methyl group looks like? What does a methyl group look like? Yeah, it's a carbon with 3 hydrogens. And what we have here is, well, carbon likes to form 4 bonds, 4 single bonds. So we have a dangling bond here. And so this is what we call methyl substituent. And so what we could do is we could just attach this methyl onto something else, because we have an attachment point here. And so, for example, we could attach that methyl group to an alcohol. What does an alcohol group look like? An alcohol group looks like an OH. And this would be called methyl alcohol. Methyl alcohol has another name. Methyl alcohol looks like methanol because it's like methane, except it has an alcohol group replacing one of the hydrogens on methane. So this is methanol or methyl alcohol. There's another name for methyl alcohol. This is called wood alcohol. Do you know what wood is made of? Interestingly enough, wood is made up of glucose. Glucose is another alcohol, but it's a sugar alcohol. And so wood is made up of a glucose, but the glucose are linked together to form a chain. And the way they're linked together, they're made in such a way that we can't digest wood. You know, if you eat wood, that's good for fiber, I guess. You know, maybe it's good for your digestive system, but you're not going to digest it, right? But to termites, wood must taste very sweet because it's just made up of sugar, right? Well, you know how a lot of people make alcohol? They ferment sugar. That's what I did. When I took organic chemistry, that was one of my favorite experiments that we did in class. You just got a bottle, you put a balloon on top of it, put a bunch of sugar in there, yeast, and then let it ferment. And pretty soon you could see the balloon start to grow bigger and bigger. And then once we got some alcohol there, then distilled it and made some like homemade moonshine, which was pretty cool. And collected in a little vial. And so, anyway, but we use real sugar like glucose, and actually, you know what sucrose is? Sucrose is table sugar, and table sugar consists of a glucose molecule bonded to a fructose molecule, and then you can digest it. Well, a lot of people think, well, wood is made up of glucose, and you can ferment sugar, and so some people try to ferment wood, and it's possible. You can ferment wood, but you don't get ethanol. Do you know what you get from fermenting wood? Methanol. You get wood alcohol. The problem, though, is you don't want to drink this stuff. This is not an urban myth or an urban legend or whatever. You can go blind permanently from drinking wood alcohol. Did you know that? Because wood alcohol, when you metabolize it, it makes formic acid. Do you guys remember what formic acid, another name for formic acid is? Methanoic acid. Methanoic acid has how many carbons? Meth. One. And it's an acid, so it's going to have the Cu group. The Cu group is the carboxyl group. And it's going to have a carbon double bond and a carbon single bonded here.
Do all acids have?
All carboxylic acids have this. So methanoic acid, formic acid, acetic acid, vinegar. Butyric acid is in your stomach. Butyric acid has a very bad smell. But this is one carbon alcohol, but carbon likes to form a total of 4 bonds. We have one double, and that means we need 2 single. And so what we do in organic chemistry is we just fill the remaining bonds with hydrogen. And so that's what we'll do here. And so this is formic acid. And apparently formic acid attacks your optic nerves irreversibly. And so it can cause blindness. So if you consume wood alcohol in any large quantity, it leads to death. And unfortunately, actually on Wikipedia, I think they keep a database about how many deaths. NIH does this too. Let's see. Oh, this is 1993 to 1998. I think Wikipedia is more current. So let's see. In Australia, 2013, 3 people died and suffered partial blindness. Homemade alcoholic beverages containing methanol. 2 people in Central Australia. Brazil, 35 people died. 450 people hospitalized.
Can it be formed from other things? Like maybe these people weren't trying to make it from wood?
Yeah, probably. I don't know. I'm not sure. You can form because certain reactions. Costa Rica, 25 people, 2019. That's fairly recent. There was something that was really recent. Let's see if I could find it. How about in the U.S.? India, 2024. I think this was that. 65 deaths in India. Don't drink alcoholic beverages in India, I think 65 deaths. Even in Ireland. Mexico, 35 people died in 2020. But this is, fortunately, it's just one not fortunately, but just one event. So it wasn't widespread. But what about the U.S.? Russia, I know, has a lot. 2023, 30 people died. U.S. 2018, oh, this is a sad one. I remember reading about this one. A Massachusetts man died after ingesting alcohol that was contaminated with methanol. Actually, the hand sanitizer, some manufacturers of the hand sanitizer, they said it was ethanol, but actually the hand sanitizer contained a lot of methanol. And the FDA came in and then shut down those factories that had a high percentage of methanol in their hand sanitizer. Contaminated with, the product consumed was labeled ethanol extraction. 95% ethanol is what you get from distillation. So this is what I made in Chem lab. I tasted a little bit. Unfortunately, I didn't die because there was no methanol in There shouldn't be any methanol. When you distill it, you can easily distill out the methanol. Distillation is a purification thing, and this is as pure as you're going to get by distillation. If you want 100% ethanol, you have to extract the water separately. You know? And so in lab, we use 95% a lot and 100%. 100% requires a little bit more work, but the alcohol that we have in lab, to prevent paying consumption tax on it, they denature it. In other words, what they do is they just put some kind of carcinogenic chemical in there so people don't drink it. You know, so it's called denatured or something.
You said that you can distill the methanol.
Yeah. For me, there's no worry that there was any methanol in there, because when you distill it, methanol has a totally different boiling point than ethanol.
Does that have to do with how many carbons are in
Oh,
it?
yeah, totally. How many carbons and the intermolecular forces. So it's pretty easy to purify. It's pretty easy. So if this person had distilled their stuff that says ethanol extraction 95%, 5%, you know, they would have been okay if they had distilled it. An FDA recall was issued, and the company is no longer selling the product, which was sold over the internet and shipped by the U.S. Postal Service. So people are trying to get this. This is like, if you go to Nevada, you can buy this, like Everclear. Have you heard of that? Everclear alcohol. It's like 95%, 180 proof alcohol or something like that. They don't sell it in California. But yeah, this was a pretty sad story, because you know this person, I don't know, was thinking they're getting a legitimate product, but you never know what you get over the internet. You know. Also, this happens in the lab. You know, at MIT, there's this laboratory there. I think it's a national laboratory called the Lincoln Laboratory. There's a very famous story about the Lincoln Laboratory. There's a group of physicists studying the electronic properties of this material. And they spent about 15 years studying this and had a whole bunch of papers published about it. And then, but during all this time, they didn't realize their samples were contaminated, because they just bought it off the shelf and somehow it got contaminated. And so finally somebody analyzed the samples. They're physicists, so they don't usually do the chemical stuff, you know. They just take the work. So, you know, after that case, when we go into lab, like when I was working in research, the first thing I always did was make sure my starting materials were what they said they were. You know, whether it's pure or mixture or something, I would analyze the starting materials first. Otherwise, I didn't want to waste a whole bunch of time in case those were heavily contaminated, or you don't know. A student might have grabbed that bottle and cross-contaminated it with other stuff. You know, put a spatula on something and then put that spatula here without cleaning it. You know, that kind of stuff happens through sloppy or poor technique. And so, just something that we do. But you know, this is labeled. And you trust it. If it's from a large chemical company, I would trust it. You know, because normally when you buy chemicals, they have a chemical analysis sheet telling you what the major impurities are and how much of those you can expect. Okay. So you don't want methyl alcohol. If you're going to drink alcohol, you don't drink rubbing alcohol either. Well, rubbing alcohol is probably not good. It's good for cleaning stuff, but don't use it. But at least you won't die if you consume, you know, small or moderate amounts of ethanol. Ethanol, I mean, fruits, wine, etc. Let me try to get this moved over here. But you can also, of course, you can also die from too much ethanol. And so there are things that are generally regarded as safe up to a certain extent. You know, too much of a lot of things could potentially be lethal. We in laboratory we find out about these types of things, in laboratory, we look for the SDS or the MSDS. Do you know what MSDS or SDS stands for? SDS, let's look up the SDS for methanol. Now this is supposed to be, when you buy some methanol, this comes included with it, and it gives you a bunch of stuff, like emergency telephone numbers, if there's some kind of poisoning incident, you know, what to do, etc. Of course, it's flammable, it's toxic. Usually they give us a what they call lethal dose, LD50. Let's take a look. But toxic if inhaled even. I mean, you don't even have to drink this stuff. That's why like hand sanitizers with methanol, not good. Are you guys familiar with the NFPA, National Fire Protection signs? You know, what's the worst? Like 0 is not bad. And what's the top of the scale, the worst? A 4. If you see a 4 that's bad, stay out of that lab, most likely. You want to be careful entering that lab. And for example, the blue is health, the red is flammability, orange, oftentimes you don't see orange, and yellow is personal protection, and this is different depending on what category the chemicals are. There are a whole bunch of symbols that they use, but those are the NFPA signs. Some first aid measures after inhalation, move exposed individual to fresh air, etc. These are standard first aid measures for most chemical exposures. After skin contact, wash affected area with soap and water. Rinse, flush exposed skin gently using water for 15 to 20 minutes. Seek medical attention. So if you spill a whole bunch of methanol on you, you want to make sure you wash thoroughly. After swallowing, rinse mouth thoroughly. Do not induce vomiting. Have exposed individual drink sips of water, dilute mouth in water, or with water or milk after rinsing. Get medical assistance. But here it talks about, you know, nausea, headache, fatal, blindness, etc. But you look at some of these, and it's hard to get a perspective, because when you look at some of these, like salt, you know, sodium chloride, and it's talking about different stuff, sometimes it's hard to get a good gauge of how hazardous it is compared to other chemicals. Fisher is one of the big chemical companies. Fisher and Aldrich and this is Sigma Aldrich. Those are two big chemical companies. So when we look at this, these are all formatted differently depending on what chemical company you get. But, you know, it's a category 2 carcinogen, ethanol. Still people drink it. Serious eye damage, eye irritation, category 2. Signal word, danger. And so it's hard to get a gauge on how serious, you know, the hazards are. You know, lots of people drink alcohol and other stuff. And so when you read this, it all kind of starts sounding the same. You don't want to touch it, etc. All right. Yeah, okay, here. NFPA health hazards are 3 out of 4. Okay. We're going to keep moving here. So, ethanol, well, that was the methyl group. The ethyl group looks like this. Ethyl group has 2 carbons. I should tweet this. How we draw this depends on if you want to try to draw like more 3-dimensional or less 3-dimensional. So if we take an ethyl group like this and add an alcohol, then we'll have ethyl alcohol. We can flatten this out. You know, this is tetrahedral, but what I'm going to do is I'm going to flatten it like a pancake here. Obviously, you can't flatten the molecule, but you can flatten the drawing. This would be ethyl alcohol. Or ethanol. This is called grain alcohol. So you could take corn or rice or wheat and make alcohol, barley, etc. All right, so the first thing is we need to extract all the conversion factors. So one conversion factor is 0.10 grams of ethanol. Ethanol, people abbreviate ETOH per 100 milliliters of blood. And so it's important that you keep the labels on everything. This is not 100 milliliters of alcohol. This is 100 milliliters of blood. In many jurisdictions, a person is considered legally intoxicated if their blood alcohol content is 0.10%. Suppose that a 68 kilogram person, okay, this is an extensive property, 68 kilogram person, has a total blood volume of 5.4 liters.
What's extensive?
I'm sorry? Extensive versus intensive.
Yeah.
And so extensive means it depends on the amount. Kilograms depends on how big the person is. This would be more this is more intensive. So for every 68 kilograms, we estimate 5.4 liters of blood. That would be more intensive. Here. And breaks down the ethyl alcohol at a rate of 10 grams per hour. How many 145 milliliters of glasses of wine, consumed over 3 hours? So we have 3 hours, that's extensive. $145 milliliters glasses of wine. So we're going to have 1 glass is equal to 145 milliliters. This is intensive. Assume the wine has a density of 1.01 grams of wine per milliliter of wine. And is 11.5% ethyl alcohol by mass. That means we have 11.5 grams of ethyl alcohol, ETOH is the standard abbreviation for ethyl alcohol. By mass, so this is 100 grams of wine. The rate at which ethyl alcohol is broken down varies dramatically from person to person. The value given here for the rate is realistic but not necessarily accurate. So I have a whole bunch of intensive things. And so when I do this, problem like this is intensive. 68 kilograms per 5.4 liters of blood, that's intensive. One glass is 145 milliliters, that's intensive. 10 grams of ethanol per hour is intensive. This is intensive. This is intensive. What's extensive? What's extensive is this, 3 hours of time. So normally when we do dimensional analysis, we start with an extensive property first. And so I would probably start with maybe 3 hours. Should we do that? There's no right or wrong. You just try it. If it fails, no big deal. If it fails, then you start over again. And so the thing that surprises me on the test is people not even bothering to try to start. You know, it's like, let's say they're lost. Well, I can understand if let's say you're lost in the desert or you're lost in the jungle or something. I can understand freezing and staying because maybe somebody's going to come to rescue you. But on an exam, nobody's going to come to rescue you. You're going to have to take some action. That is, you're going to have to move. And so, you know, usually we start off with an extensive, but you don't have to. You could try to start with an intensive. But the easiest is just to start off with an extensive property and then you don't even need to know where you're going. So let's start off with 3 hours. We know that's fixed. And then we know we have an hourly consumption. For every 1 hour, 10 grams of ethanol are digested or consumed. But will this get us to the right place? We have to think about that. You know, sometimes we'll have to add things to this. But I don't necessarily know where I'm going, you know. Mm-hmm.
Does the rate increasing or decreasing has to do anything with dimensional analysis? Like, we have to...
The rate throws in a wrench into my dimensional analysis scheme here. You know, if I really thought ahead on this, I probably wouldn't solve it like this. You know, I'd use a different thing because, you know, what I'm doing here is this is going to tell me how many grams of ethanol are consumed in total. But I don't want to consume all that ethanol. I want to leave some ethanol left over. How much ethanol do I need to leave left over? I need a blood alcohol of, what are they saying? I need a blood alcohol of 0.10% at the end, you know. And so I need to leave some stuff left over. Well, we could figure that out. We could do this in 2 steps, you know. So if I start off like this, this is going to tell me how many grams of ethanol I'm going to consume in this time period. And this will tell me how many glasses of alcohol will be, actually glasses of wine will be completely digested, like all the alcohol will be digested. And so we could do this and that will tell me how many glasses, but to this many glasses, I have to add some more glasses of wine to get that blood alcohol to 0.10%. Does that make sense? And so we could just do this really quick here. Okay, so hours cancel. How many? And there are multiple ways you can solve this. When probably ask some of the students here how they solved it, they probably solved it a different way. Okay, so we get how many grams of ethanol, and then what was the wine's ethanol content? The wine's ethanol content was, what, 11.5 grams? Per 100 grams of wine. the grams of ethanol. Now I have grams of wine, and then I know the density of the wine. The density of the wine is going to be a little higher than water. It's 1.01 grams. Obviously, there's other stuff in wine than just water. And so it's 1.01 grams per milliliter of wine. And so now I have milliliters of wine, and then I know 1 glass of wine contains 145 milliliters. And so this tells me how many glasses of wine I can have that are going to be completely digested. And so I would do 3 times 10 times 100 divided by 11.5 divided by 1.01 divided by 145. And that gives me 1.78. So if you have about 2 glasses of wine in 3 hours, your blood alcohol should be 0, assuming that it's close. So this is why they say, like, 1 drink in 2 hours, you should be safe to drive, right? Something like that, or 2 drinks in 3 hours or something, depending on how fast you metabolize it. But that's to be like a blood alcohol of 0%. This would give you a BAC of 0%. We're okay with a BAC of 0.1%. And so we look at the one person, and this one person is going to have how many liters of blood? 5.4 liters of blood.
How do we solve the first thing? The 1.78 glass.
I'm sorry?
Like, do we solve the first thing with the 1.78?
You could solve it in different ways. This is just one of the ways. I'm trying to make it a little simpler. I probably would have done this as a combined, 2 algebraically combined. The problem is you drink the alcohol and automatically your body starts digesting the alcohol. And there are a lot of calories in alcohol. So there's a classic, have you heard of the beer belly? People who drink lots of beer, they get a lot of calories, not just from the beer, but from the alcohol itself. And so a lot of calories from that. And so, anyway, this is to figure out how much of the alcohol will be completely consumed in 3 hours. But we're safe. We're safe. But we're safe here completely because we should be at 0%. So if you did a breathalyzer test, let's say, you're at 0. You're 0%, right? But you would still be legal at 0.1. So that's why we did this. Now we're going to figure out how much extra can you have. So after 3 hours, I'm going to have a little bit more, than 1.78 glasses. Let's say can I finish that second glass of wine, or should I hold off? If I finish that second glass of wine, is that going to throw me over 0.1% or not? And so we can figure that out. We can figure out how much more alcohol we can consume to bring our blood alcohol. It depends on your volume of blood. So 5.4 liters of blood. And then we want a blood alcohol of 0.10 grams. This is per milliliter. Let me convert from liters to milliliters. 1,000 milliliters per liter. This gives us milliliters of blood. And then we're allowed 0.10 grams of ethanol for every 100 milliliters of blood. And so that gives me grams of ethanol. And then I know that there are 11.5 grams of ethanol per 100 grams of wine. And then the density of the wine is every milliliter contains 1.01 grams. This is for the wine. I'll just write wine here because I'm running out of space. And then 1 glass is 145 milliliters. So this will bring, let's say, after 1.78 glasses in 3 hours, this is how much extra you can drink right at the end before driving and still be legal. Actually, you want to be under this. And so we go 5.4 times 1,000 times 0.1 divided by 100 times 100 divided by 11.5 divided by 1.01 divided by 145. 0.32. So you could finish that second glass. It was 0.32 glasses. And so altogether, how many? It's 0.32 plus 1.78, 2.10. glass. You want to go under 2.10, but then you don't know how fast your body metabolizes it. You know, it depends on your blood volume and also other things. Like some people have a hard time metabolizing alcohol genetically. And then there are people who can drink. And, you know, some of my friends could drink like 2 12-packs in one day. That's something I couldn't do. But they metabolize it very fast. I mean, but I'm glad I can't do that. Otherwise, the budget would be break the bank. Especially, I mean, I went to Big Bear. I had a beer. What was it? It's like $12, I think it was. And then you add in tip. That's just one. And so if you're metabolizing the alcohol that fast and you need a 12-pack, that's like going to be expensive. But anyway, go on here. So this is dimensional analysis. This one is a complicated problem because it wasn't just one step, it was 2 steps, and you had to think about it for some time. Okay, were there any other questions?
Yes.
On this is chapter 1. There's chapter 2, 3, and 4 by next week. Our test is on Wednesday, so be aware. If you haven't started chapter 1, you probably want to start it ASAP, you know. Because this is just one of the problems in chapter 1. It might take you. The situation is this. If this problem starts taking a long time, what do I mean by a long time? You know, I remember being a student and some of the problems, especially like physics, takes 1 hour, 2 hours, 3 hours. I'm thinking into one single problem. That's not enough. You don't have enough hours in the day to do it. And so this is why I recommend, and this is the way I do it, is if it starts taking too long, like you can't figure it out, don't waste time. If you're spending 1 hour on this problem, I think that's a waste of time. I think what you should do is I think you should just look at the solutions guide. The complete solutions manual's out there. You can just look at the solutions guide and then see it. Because maybe what you need is you just need more practice or you need more examples. It's like, let's say you're a forestry person, you're studying the forest. So you're on a summer program and you're going out to the forest to study it. And let's say you spend the entire summer studying just one tree. And if you spend the entire summer studying one tree, you're missing the whole forest, right? Well, that's the way I think about it. If you're spending all your time on one problem, you're missing the whole forest. What you want to do is, even if you don't, you know, you might be the biggest expert on that one tree, but your job was to study the whole forest. And so it's the same thing in chemistry. You don't have to be an expert on blood alcohol. You don't want to spend 5 hours on this particular problem. What you want to see is you want to see the whole spectrum of problems that you're going to get. So when you look at the forest, you want to see the biodiversity here. Maybe it's only one tree in the entire forest, a monoclonal forest or whatever they call those. You know, it's like for making wood. But the same, the situation here is what you want to expose yourself, and this is what you want to expose yourself to the widest spectrum of problems that you can, because then you won't be surprised on tests. You know, this is why when I prepared for exams, I looked at every single problem in the book, because I didn't want, you know, if you look at every single problem, then you see every single variation of the concept, you know, at least that the authors could think of. And so there might be more variations, you know, there might not be. There might be twists, you know, this and that particular problem. But I didn't like master every single one. I have a different philosophy. I know a lot of professors, and I was taught this too, you know, never look at the solutions guide. The solutions guide is the last resort. And I adhered to that. And then I thought, I'm wasting my time. And so I didn't do that. I started looking at the solutions guide. And this is what we do in beginner classes. Of course, in advanced classes, you want to be able to solve it yourself. But when you're beginning and starting out, then you want as many tools in your tool chest as possible. You know, you don't want to have to fix a car with all the complex fittings and with an adjustable wrench. You know, you want as many tools as possible. And the more tools you have, then you got specialized tools, and the easier it's going to be to fix things, and the easier it's going to be to problem solve. And so that's my philosophy on this. Yeah, of course you want to avoid using the solutions guide, but also, you know, to back that up, I did this early. When I looked at the solutions guide, I did it early. I did it early because I have bad memory. I did it early so I could review, and so I had a homework notebook, which I used to make people maintain a homework notebook, and a lecture notebook. And I'd review both. Like I said, when I reviewed for tests, I started from day one reading my entire notes. It was easy to memorize because you reread it every day. It's easy to memorize. And then I'd do the same with my homework notebook. I read through the problems and then just made a mental note. So I had a little mental library about how to solve these problems. So if a homework problem came on the test, I thought it was great, because those were easy points. I could solve those very easily because I already had those memorized. And if a problem that I'd never seen came on the test before, then usually it was just a twist or combination of two problems I've already seen, so it wasn't that hard, you know. For most, you know, some things are just hard, like thermo, it's just hard. Too many relationships to keep track of, it's hard. But it works effectively for other things. What was the other question?
It's
Chapter 3? Okay, chapter 3.
Formula.
And then do you recall, it was, can you read out the question?
Yeah, I did the parts A, B, and
Oh.
was correct, but the C is I trouble.
Does it give you the corresponding problem in the book, like the number in that particular one, or?
It's 1C.
I mean the number.
Oh, it's 2.
2. Does it give you like a?
2A, formula for formula.
It's the question with, they give you the atoms and you have to make the formula out of it.
Oh, okay.
I know that question got me.
All right, 2A.
Yeah.
This one?
Yeah, it gives you like the, I think it's the next one.
Yeah, the next one.
This one has a common name too, but this would be dinitrogen tetrahydride. It's called a hydrazine. This is the fuel for like rockets. You know, Toyota. I mentioned Toyota is looking at using ammonia as a fuel. This is very similar to ammonia. This one?
No, it was,
This one you guys should recognize. What is this? This one always reminds me of a dog. And if I just twist this one, so these four like this, we can twist the single bonds. but then this would be the tail and this would be the blade. So.
Hydrogen and carbon.
But what is this one?
Is that
Ethanol. This is ethyl alcohol. CH3, CH2OH, ethanol. This one?
It didn't use pictures, it used, like, just description.
Oh, description.
I could just give one. The picture one was one I showed. That other one was.
Well, we could do that since I have limited time. In Chem 1A, I have limited time. Chem 4, there's a lot more time. So we'll take a look at it. Just come, you can come to the office. I have the office hour online. Like last night, I had it 9:30 to 10:30. It's a little late, but you can come to that or stay after class today. I have an office hour after class. We'll look at these problems then. I'm going to just continue because I got to finish up chapter 3 and then go on to chapter 4. So a lot of chapter 3's review of nomenclature. And so I'll let you review this. The acids, I have a different naming system for the acids for both polyatomic and monatomic. And so the naming system that I use for acids, I'll just look at here. It's the cation's always the same, and the anion is different. We usually call X minus, and when we look at the anion, it could be XX minus or whatever, XY minus, but or minus 2 even, or minus 3. But the anion, we only have 3 endings for anions. We have the "ide" ending, we have the "ite" ending, and we have the "ate" ending. And so if the anion ends in "ide," then HX is going to be called hydro, and then the name of the element, ic acid. If the anion ends in "ite," then we call it the "aus" acid. And if the anion ends in "ate," we call it the "ic" acid. And so there are only 3 possibilities for acid names: the hydroic, the aus, and the ic. So let's take a look at these. So this is fluoride. So we get, yeah. Good? Okay. So F minus is fluoride, hydrofluoric acid. Br minus is bromide, hydrobromic acid. Cl minus is chloride, hydrochloric acid. I minus is iodide, hydroiodic acid. S2 minus is called what? Is sulfide. And so this is called hydrosulfuric acid, hydrosulfuric acid. Most people call this hydrogen sulfide, aqueous hydrogen sulfide, or hydrosulfuric acid. The hydrosulfuric acid, is that a strong acid? If it's not one of the 7 common strong acids, it's weak. That's a rule. That's not a law. And so most of the time you'd be okay. Sometimes you'd be wrong. What anion is this? And so what is this called? Now, we have 2 names. If H2S is a gas, we don't call it hydrosulfuric acid. If H2S is a gas, we call it hydrogen sulfide. More properly, it should be called dihydrogen sulfide, but nobody calls it dihydrogen sulfide. Everybody calls it hydrogen sulfide. HCN gas is called hydrogen cyanide. But HCNAQ is not. HCNAQ is called what? Yeah, that's correct. Hydrocyanic acid. Hydrogen sulfide is lethal. There are deaths every, I think, I don't know, every year. The last death I remember from hydrogen sulfide exposure was in Ventura. Out one of the, was that it? You know, there's a lot of drilling out there for oil. So it's one of those drilling sites. Hydrogen cyanide has a kind of an infamous. This has been used in California to execute people. You know, this is hydrogen cyanide gas is the gas they use in the gas chamber. Hydrogen sulfide is rotten egg. Hydrogen cyanide is burnt almond. So if it smells like burning almonds, I don't know, maybe get out of there. Unless you're roasting almonds. So let's look at some acids. Acids will take the anion and add an H+. So CH3COOH. That would be called acetate makes acetic acid. Carbonate would be two H's. So it would be H2CO3. Carbonate would form carbonic acid. We can also have this. This is called an acid anion. Acid anions begin with H. And so this is like removing one of the hydrogens on carbonic acid. Hypochlorite would make what acid? If we add an H, HClO? Chlorous acid. Not chlorous, but hypochlorous acid. Chlorite would make chlorous acid. Chlorate would make chloric acid. Perchlorate would make perchloric acid. Chromate would make chromic acid. Dichromate would make dichromic acid, although you don't see some of these because the chromate and the dichromate depend on pH. One is stable at low pH, the other is stable at high pH. And so depending on what the pH of the solution is, the acidity of the solution, that switches these. Cyanide makes hydrocyanic acid. Hydroxide makes, okay, if we were to label this using our proper nomenclature, it would make hydroxyic acid. You know what I mean? So that would be another name for this. In fact, people love to play with names. And so rather than doing hydroxide, let's do oxide. Oxide would make what acid? Oxide would make hydro. Hydro dihydrogen monoxic acid. Hydro, or this is oxo, yeah, hydroxyic acid. Hydroxyic acid. Hydroxyic acid. This would be called hydroxyic acid. Sounds dangerous. And let's take a look for hydroxylic acid. Yeah. Yeah, hydroxylic acid is another name for dihydrogen monoxide, a parody name for water. Can we drink hydroxylic acid? Etc. The other thing is they try to have all the names on things like the CRC. So when you look at the CRC or the Merck index, they try to list all the names that you might find for different things. Nitrite would make nitrous acid. Nitrate would make oxalate would make. Permanganate would make permanganic acid. Phosphate would make, it should be phosphate, but historically it wasn't known as phosphoric acid, so they changed the name. Phosphoric acid. Sulfite would make sulfurous acid. Sulfate would make sulfuric acid. And then we have acid anions, depending, for these polyprotic acids. We can have acid anions. You guys are familiar with acid anions, correct? Like, for example, HSO4 minus. HSO4 minus is called hydrogen sulfate ion, or bisulfate. It's more commonly known as bisulfate. Thiosulfate would make thiosulfuric, or no, yeah, thiosulfuric acid, H2S2O3, thiosulfuric acid. The two most common acid anions would be hydrogen sulfate or bisulfate, and this one, hydrogen carbonate or bicarbonate. Those are extremely common.
I have a question when we refer to things as like the things with ions, like when we talk about bisulfate, is it that it has like one extra charge, like a negative one charge?
H plus is positive, so you have to cancel out one of the negative charges. So carbonate is -2. And then if you add an H plus, you cancel out one of the negative charges. So HCO3 is -1. Is that what you were talking about?
What is it?
Carbonate is -2, so bicarbonate is -1 because you have one H plus canceling out one of the
But
negative
does that
charges.
apply to everything when
Everything, yeah.
if it has a negative one charge?
Yeah, like for example, this has -2, so we need two H's to balance out the charge.
If it doesn't have one H,
Then it would make a acid anion. If you only had one H on here,
Yeah.
you'd form HCr2O7 1 minus.
what would that become?
That would be called hydrogen dichromate ion or dichromate. Yeah, something like that. Yeah. Bi usually stands for these acid anions. Di with a D, that usually refers to 2. Bi should refer to 2 too, but we use it for these acid anions here. All right, so that's the end of the nomenclature that I was going to talk about. I mean, you'll probably want to review some of the Chem 4 nomenclature since I skipped over some of the stuff. But the other thing we're going to talk about is how to determine the composition. The formula tells us the elemental, atom by atom composition. And so we're going to talk about how to determine these. So if we look at something like this, halothane, it's got a lot of halogens, but we don't have to worry about naming this. But we can get the composition by atoms, 2 fluorine atoms, 1 chlorine, 1 bromine, 2 carbons, 1 hydrogen per molecule. But how is that determined? And so the way we determine formulas or composition, let me talk about that now here. Sorry, this is out of order, but I wanted to go in this order here. And so let's say we had some unknown here. And what we do is we send this out for chemical analysis. Or you could do the chemical analysis yourself. A lot of the chemical analysis comes from expensive instruments. So if you don't do a lot of chemical analysis, it's not worth buying it, and so you just send it out. And so as far as different types of chemical analysis goes, we have elemental analysis. And elemental analysis is either going to give you grams of each element, in, you know, a given amount of sample. So let's say you send out a 10-gram sample or a 100-gram sample, and they'll tell you how many grams of each element are present in there. And there's different techniques for different elements. And so some elements are easier, some elements are harder, and so the cost per element varies. And it can get expensive. I sent out some samples because I wanted to know what the composition of this stuff I made. You know, I was trying to make new stuff. And so, first thing I wanted to do was figure out, you know, how much of each element was in there. I sent it out to this place in Gardena. There's a lab that does this. Cost at the time, this was decades ago. The cost was about $200 per element, but now it's probably even more. So I had to give them a list of elements to analyze for. Otherwise, if they're looking for the whole periodic table, it would be extremely expensive. Or percent composition. So here, they can either tell me how many grams of each element in, let's say, 100 grams of sample, or just the percent composition. This is like typical. We have another type of elemental analysis. This is called combustion analysis. You know, this is for carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, etc. And these are typically organics, because organics are, a lot of them are flammable, like ethanol, and etc. And so we burn this. And then from this, we can get the, what we end up getting from this is the different things. Let me talk about this. What we end up getting is we end up getting grams of CO2, grams of water, grams of etc. from this. And then what we do with this data is we get the formula. The formula is the mole ratio or atom ratio or dozen ratio, whatever. It's the ratio. Mole is just the counting unit here. And we have two types of formulas. We usually end up with the empirical formula here. Or formula unit. And this is fine. If it's ionic, we stop here. Ionic or network covalent. However, if it's molecular, then we want to go one extra step. Then we're going to need one more piece of information, and that one more piece of information would be the molecular mass from mass spectrometer or whatever. There are other techniques that are used to get the molecular mass, etc. And then what we can get is the molecular formula from this. So if we have a molecular compound, we'd like the molecular formula. If we have an ionic compound or network covalent, then we'd like the empirical formula. So do you guys remember calculating the, well, this is calculating percent composition from a chemical formula. And so for example, water, we do the average, and so the percent hydrogen is going to equal 2 times 1.008 divided by the total mass of this, which is going to be 18.02 times 100%. And then we can get the percent oxygen. This is going to be 16.00 divided by 18.02 times 100%. And so it's just grams of oxygen over total grams, etc. Do you guys remember doing this? So I'm not going to cover this. This is Chem 4. Do you guys remember solving the empirical formula from either the percent composition? Yeah. From the percent composition, you assume a 100-gram sample. Then you get the grams of carbon, grams of whatever. So I assume you've all done that. So what we're going to do is we're going to look at the combustion analysis. So this is figuring out the empirical formula from the percent composition. We assume 100 grams, we get the grams of each element. Then we figure out the moles, and then we get the mole ratio. We end up with the empirical formula. The simplest mole ratio, whole number mole ratio, will be the empirical formula. What we're going to do is combustion analysis. You may not have done this here. We can start off with a hydrocarbon, which would be carbon and hydrogen, or an alcohol, which would add in an oxygen, or an ether, or there are a whole bunch of groups, carboxylic acid, whatever. And so we might have some oxygen, we may not have some oxygen. In combustion analysis, a lot of these organics burn. And when they burn, we do complete combustion, and all the carbon gets converted into CO2 here. So let's say I started off with 10 grams of carbon here. I'm going to end up with 10 grams of carbon in my CO2. Atoms are neither created nor destroyed. And so all the carbon that ends up in CO2 came from my original compound. So we can figure out how many moles of carbon I had in there. X would be the moles of carbon that I need in the simplest ratio here. By going from grams of CO2 to moles of CO2, moles of CO2 to moles of carbon stop there. And that gives me my X. Now the Y, the moles of hydrogen and the mole ratio here are going to come from all the hydrogen ends up in water because we're combusting it with oxygen. So the hydrogen is going to end up with the oxygen and H2O. And so we can figure out what our Y is by taking how many grams of water we form, going from grams of water to moles of water. Moles of water to moles of hydrogen is a 2-to-1 ratio. Moles of hydrogen is our Y. Now our Z is difficult because our Z depends, because now the oxygen here doesn't come from Z. The oxygen here comes from Z and this, which we'll call XYZ without. So I'll call this W. W, and so this is going to be a mix of W and Z. And this is going to be a mix of W and Z. Does that make sense? We lose track of the oxygen because now the oxygen we get in CO2 and water comes from two sources, our original unknown and the oxygen that comes from air. And so oxygen makes it a step harder. However, if our sample doesn't contain oxygen, it's straightforward. And so we have to be given some pre-information. Somebody has to tell us if this compound contains oxygen or not. But it's easy to determine. It's easy to determine by the infrared vibrations. You know, I talked about motion. One of the motions are vibrations, and oxygens vibrate at a different frequency than other atoms do. And so by looking at the infrared deals with vibrations. You can easily determine if you have an alcohol in there or something else like that. And so they told us this sample contains carbon, hydrogen, and oxygen. This sample, do you recognize this sample? We already know what it is because they told us the formula. What is this? Well, it's how many carbons? 2 carbons, and you see this OH is, what's OH called? Not a hydroxide, because it's a carbon bonded to an OH. If it were metal bonded to an OH, we call it a hydroxide. But a carbon bonded to OH is a covalent bond. It's not ionic, so we don't call it hydroxide. We call it, it starts with an A. Yeah, alcohol. And so if we take a sample of pure ethanol and put it here as a liquid and then just catch it on fire, then all the carbon in ethanol ends up in CO2. So over here we have 2 carbons of ethanol. Those end up in the CO2, so we'll get 2 CO2s for every one of those. And then all the hydrogens, these white ones, end up in water. So we have how many hydrogens? 3 plus 2 is 5 plus 1 is 6. So we end up with 6 here. Now the oxygens get mixed up because we have 2 sources of oxygen, air, and this. And so what we're going to do is we're going to figure out, we're going to weigh the sample. How many grams of sample do we have? And then we're going to figure out how many grams of carbon were generated. And then we'll figure out how many grams of hydrogen. So we don't stop at moles. When we have oxygen, we go all the way to grams. And so we're going to go from grams of CO2 to moles of CO2, moles of CO2 to moles of carbon to grams of carbon. And then for the water, we go from grams of water to moles of water to moles of hydrogen to grams of hydrogen. And so the total mass, this is 2 equations, 2 unknowns. The total mass here is equal to the grams of carbon plus the grams of hydrogen plus the grams of oxygen. And so by taking the total mass and subtracting out the carbon and subtracting out the hydrogen, we're left with oxygen. So we're going to figure out how many grams of oxygen we have by subtraction. Once we get the grams of oxygen, we're going to convert that to moles. And then we're going to go back to the moles here and get the simplest mole ratio. But it's already done for us because they told us what it is. This is just showing the concept, how it works. So let's take a look at the actual problem using combustion analysis. We'll take a look at two problems using combustion analysis here from chapter 3. Actually, we should look at all the problems involving combustion analysis. That way you get no surprises, right? So if we look at a 0.1888 gram sample of hydrocarbon. Hydrocarbon, is there any oxygen in a hydrocarbon? There's no oxygen. A hydrocarbon only contains hydrogen and carbon. If this were an alcohol or sugar or something like that, then there'd be oxygen. And so a 0.1888 gram sample of hydrocarbon produces 0.6260 grams of CO2. So if I produce this many grams of CO2, I go from grams of CO2 to moles of CO2, moles of CO2 to moles of carbon, stop there. And then it produces this much water. So I'll go from grams of water to moles of water to moles of hydrogen, stop there. And then I figure out the simplest mole ratio of carbon to hydrogen by dividing by the smallest number of moles. Do you guys remember doing that? And that gives me the empirical formula. Then its molecular mass is found to be 106, so this is a molecular compound. If its molecular mass is 106, then do you remember doing this? Going from the empirical formula to the molecular formula using the molecular mass. It depends on how much the empirical unit weighs. And so we could do that. This is also asking for mass percent, but we need the mass percent after we are at this. Paracresol is used as a disinfectant in the manufacture of herbicides. A 0.4039 gram sample of this carbon, hydrogen, oxygen. So now they're telling us there's oxygen here. And so we solve this differently. And so we're going to go from grams of CO2 to moles of CO2, moles of CO2 to moles of carbon. But we don't stop there. We're going to go from moles of carbon to grams of carbon. The reason we're going to go all the way to grams of carbon is we have to figure out the grams of oxygen by subtraction. So once we know how many grams of carbon we have, we do the same thing. We get the grams of hydrogen, subtract out the grams of carbon and the grams of hydrogen, and what we're left with is grams of oxygen, and then convert everything to moles, get the simplest whole number mole ratio, and then we have the empirical formula. Great. Let me talk about just one more here in the last second. This is dimethylhydrazine, is carbon, hydrogen, nitrogen. So the carbon ends up in CO2, the hydrogen ends up in water, but where does the nitrogen end up? And so in this process, they convert the nitrogen into N2 gas. So here, it's easy. All this N2 came from this. And so we just convert this to moles, and then we get the mole ratio. Sulfur and phosphorus form different products. This is sulfur. Sulfur gets burnt to SO2. Phosphorus gets burnt to something else. But it's the same concept if there are other elements in there. It's just figuring out the moles of the elements. Yeah, stop there. Uh-huh.